We are glad to start today's program organized by the Academic Trust, the Indian Academy of Sciences, in association with the DAV Narela School, DAV Centenary School, Narela. And we are very thankful to the DAV Centenary School, Narela, for giving us this chance to interact with the young minds who are future of our country. There are 4 talks planned in this. So a couple of talks were there yesterday, and today we have the talks on physics and chemistry. So yesterday was maths and biology on the 4 basic sciences. So today's physics talk is going to be delivered by one of the foremost physicists of the country, Prof.Bedangadas Mohanty. He's a very acclaimed physicist from the National Institute of Science Education and Research in Bhubaneswar. Professor Mohanty is a recipient of several awards and honors for his work. I will not go into the details of all that. Suffices it to say that he's a fellow of the Indian Academy of Sciences. The Indian Academy of Sciences is the one that is organizing this series of lectures. So Professor Mohanty we are very privileged to get Professor Mohanty today with us. He will tell us about certain things about the space, which are always exciting, certain recent discoveries in physics, black holes, etc. And we are looking forward to his talk. So Professor Mohanty.
Thank you, Professor Tirthankar. And first, I would like to thank Indian Academy of Sciences, Bangalore, and DAV's school for giving this opportunity to share some of the excitements in physics in last 10 years. So that's what is the title, Recent Discoveries in Physics. And these are associated to 2 great physicists or scientists of our time, Newton and Einstein, whose photos you can see on the right-hand side. So in 2012, through the experimental observation of Higgs Boson, we tried to understand what is the origin of mass. Remember, Newton was perhaps one of the earliest persons who defined what is mass. Quantity of matter is what is mass. Then in 2015, we discovered the gravitational waves. The correct theory of gravity was given by Einstein. After his special theory of relativity, he went on to give general theory of relativity and the theory of gravity. Black holes, and that was observed in 2015. And in 2019, we tried to photograph a black hole. Remember, seeing is believing. So scientists came together to do this unimaginable sort of thing to photograph a black hole. And that was very exciting. And that happened in April 2019. So I will touch up on stories at a level of 11th and 12th school children. I tend to put it as unfinished symphonies. You know, Newton wrote down many expressions related to mass, but origin of mass is something which was an open question. So that sort of got addressed by finding the Higgs boson. Similarly, although Eddington, as I will discuss, tried to show that Einstein's theory of gravity is the correct one, but the discovery of gravitational waves sort of made it more complete, and this exciting thing of photographing black holes. Before I go into the topic, just want to say that if the students wants to pursue a basic science as a career, there are institutes like NICER and ICERS who have 5-year integrated master's program in all areas of basic science. And if you want to pursue career in a basic science, then these are some of the good institutes to be associated with. one I'm associated with is Neisser, whose motto is knowledge imparts immortality. So let me first discuss about gravitational waves. So Newton, when was sharing his findings, said space and time are separate. Like space as we know, currently it's 3 dimension, and time. And there was this concept of absolute motion. Then he laid down the theory of gravitation, that if there are two bodies, as you see in the slide, of mass m1 and m2, separated by a distance r, then the force of gravity, which is attractive, is given by g m1 m2 by r square, where g is called as the universal gravitational constant. Universal because it's expected to be same everywhere in the universe, and its value is roughly 6.6 10 to the power minus 11 Newton meter square by kg square. Now, if we have two bodies of same mass, say 1000 kg, separated by 1000 meter distance, then the force experienced is 6.6 10 to the power minus 11 Newton. And that's a small force. So we don't feel it in our daily life. Even if you pass by a mountain, it has this force, but the force is small. But for huge astronomical objects, it's the force which is sort of responsible for planets moving around the sun, or moon, or artificial satellites moving around Earth, to the extent that also the gravitational effect of the moon on Earth is felt through the ocean tides. So this is an important force which we deal with in the nature. However, there is one issue with the Newton's formulation of theory of gravitation. It tells that as soon as you bring in two bodies, the force will be instantaneous. That means the signal of gravity will move with infinite speed. So that's the issue, because when Einstein gave his theory of special relativity, what he did is he brought space and time together. There was concepts of relative motion. And then he said that any object having non-zero mass will never move with speed greater than speed of light, or the maximum speed which we can communicate according to his theory is with speed of light. So there was this issue with the Newton's formulation of laws of gravitation. What Einstein did is try to take care of this aspect, sort of delayed the signal transmission, and gave his theory of gravity. Now what he said is that gravity is in a simpler way. I will be using examples which has, trying to tell the concepts through examples, which of course in the true sense has solid theory and a well thought out structure in mathematical formulation or scientific formulation, but I will be using mostly analogy to explain. So gravity, he said, is just a wrappage of space and time, and it's not sort of force acting at a distance. And the informations are carried by gravitational waves. What he meant by that is, he said, you imagine that space is like a rubber sheet. You can see the picture which I'm showing on the right hand side. And you have a mass on the surface. When you put a heavy object on a sheet of rubber, then you can see it causes deformation. And when another mass is dropped onto this sheet, now you are imagining the space to be this rubber sheet. There is already an object, causes deformation in the space. And when another mass dropped onto the sheet, it rolls towards that. So he theorized that smaller masses travel towards larger masses, sort of not because they are attracted by some mysterious instantaneous force, but because smaller objects travel through space that is wrapped by the larger object. That was the idea. Now, another interesting thing when he told about relativity was the mass energy equivalence, right? If that's true, then although light, which is made up of photons, which are massless, but it has energy. So if there is mass energy equivalence, then in that sense, light should be also affected gravitationally. That means if there is a ray of light coming from an object to an observer and there is a massive object in between, then light won't travel in a straight line, but it will bend. That is because the space is itself deformed because of the heavy body present. This he gave in 1916, around 1916, and then Arthur Eddington set out to try to see if he can prove this concept. So he went to west coast of Africa on a full solar eclipse time. The idea was like this, that you have a solar eclipse, so the bright lights coming from the sun will not be there. I think it was 29th May. Then you have a star on the other side, and you try to figure out where is the position of this star. And then you also know its position when the sun is not in between the star and the observer. And what he found is that the position of the star is shifted when he looked at during the eclipse time. And that famous figure is this Einstein's cross, that the apparent position of the star is shifted because light has bent and come and reach the observer due to the presence of a massive object. That was sort of first proof of the concept of gravity which Einstein said. He was so excited about this finding and he wanted to communicate to common people. So he wrote a parody, and I've just reproduced that here. It's very interesting to read, to convey this message that this is how gravity works. He said, "Oh, leave the wise our measures to collect. One thing at least is certain, light has weight. One thing, the rest debate. Light rays when near the sun do not go straight." So he used to convey this message through this interesting sort of poem. Now, coming to the gravitational waves, how they are generated. Now remember, any charged particle, when it is accelerated, any kind of charge, for example, in this case, it's mass, but in case of electricity, magnetism, it's electric charge. Whenever they're accelerated or decelerated, they emit radiations. Now, these gravitational waves are some things to deal with mass. And the way they move is they shrink the space along one axis and axis perpendicular to the wave direction as they stretch the space in the other axis. And that is shown by this sort of oscillating picture on the right-hand side. So when these waves travel, the space shrinks and expands on different directions, and that is what how it propagates. Now the question is, how do we then detect it? Now, the principle of detection is, I'll try to explain by a Michelson interferometry, which usually student in maybe +2 or BSc, they come across. The picture on the right-hand side is this Michelson interferometry setup at my institute, where you can see there are these circular interference patterns, which are produced by the students doing this experiment. The concept is simple. You have a source of light, which is on the left-hand side, the laser. Then you have a beam splitter. There are two mirrors, M1 and M2. The light goes, then it is part of it goes to mirror 2, part of it goes to mirror 1. It reflects back, and because there is a path difference, it causes a phase difference. As a result, there is an interference pattern seen on the screen. That's the concept, and you can see the actual experiment interference pattern on the right-hand side. If the two waves are in phase, as you see on the right-hand side bottom plot, on the left in phase, then the signal gets amplified. If you are out of phase, the crest and the trough sort of cancel each other, and then you do not see the signal. Now imagine you have such a setup and you tune everything to get the signal. And if there is a gravitational wave, this L1 and L2 that you see, these are the lengths from the beam splitter to the mirrors, that will change because space shrinks and expands. As a result, if you have kept your detector with a certain mode for a particular signal, and if a gravitational wave passes through, then that reference level changes. And that's what people try to see. So the basic idea is, again, build a huge Michelson interferometer. Now to build these huge mirrors, to have a proper cancellation of any other source of vibrations is itself a technological challenge, but people did it. And what I just said, you try to keep in a particular reference level, and if the gravitational wave passes through, that changes the relative positions, and then you should see deviation from your reference level, right? And then people calculated that what is the sensitivity of change in this length scale which we should be able to detect in order to detect the signal. And that turned out to be 10 to the power minus 18 meters. That is the level of sensitivity of change of lengths which you should see in order to detect the signals, and that was the challenge to build such an interferometer. And by the way, India is also setting up such an interferometer, I think around Maharashtra. Now, just to give you a perspective of the sensitivity, 1 meter is roughly 40 inches. 10,000 times smaller is a human hair. 100 times smaller than that is the wavelength of light. Another 10,000 times smaller than that is the diameter of an atom, right? You all may have read Vo radii is roughly of the order of 0.5 angstrom. Angstrom is 10 to the power minus 10 meter. So diameters are of that order. Most part of the atom is vacant. You have a positively charged small nuclei. So 100,000 times smaller is the nuclei diameter. It is of the order of femtometer. And we are talking about sensitivities which is 1,000 times smaller. That was the challenge. So not only we have to design the experiment, build the instrument, and then detect such level of sensitivity. And it was done. There were 2 such interferometers put in USA at Hanford Observatory and Livingston Observatory. And when the gravitational wave passes, and the source could be merger of two black holes or a neutron star and a black hole interaction, as we have now learned. And when the gravitational waves pass through, then you have the sensitive instruments which will lead to the observation of these waves, basically on the technique of Michelson interferometry, which I just discussed. So what I will do is now show you a video where you will see a simulation of two black holes merging, releasing the gravitational wave. It was about 1.3 billion years ago. That's how people back calculated from the signal that they got. And the frequency as a function of time, the signal is converted, and you can hear a bip of the sound, which one could in some way associate with this merger of the two black holes. And in that sense, you are going to see something which happened billion years ago. And that is really exciting that we can have such a measurement. And let me show you this video. So 1.3 billion years ago, two black holes collided and merged. This is from the LIGO website. And as they come closer, they spin more, and then they merge. And when they merge, these two massive black holes, several times larger than mass of a sun, they generate gravitational waves which traveled in the universe and reached these two LIGO detectors. And they were able to measure the signal, and when they converted it to frequency versus time, you can hear it. Just note it. That's the sound. That's what reflects the merger of the two black holes 1.3 billion years ago. Isn't it exciting? You can see and measure some things which had happened so early in the universe formation, and that level of sensitivity, precision, and physics ideas has been put to test. So that was, of course, it was such a interesting findings, sort of proving the true theory of gravity, that it had worldwide media attention. All countries covered it. And it was such a profound measurement that in 2017, for their decisive contributions to this interferometry detector and observation of gravitational waves, the three scientists here on the right-hand side were awarded the Nobel Prize in Physics. So that's the first story of detecting the gravitational wave. Now we move to the next story of origin of mass. Before that, let me tell mass about which particles. I'm talking about mass of fundamental constituent of any matter that you see around. That means the matter is made up of these fundamental objects which are not further subdivided. Little bit of history. You all must have read the school and colleges, the Dalton's theory, atomic theory. And at that time, it was believed that atom is the fundamental constituent of matter. Atom by itself means, it's a sort of a Greek word. I think it means undivisible, or which cannot be cut or subdivided further. Later on, it was found by Marsden and Geiger, working in Rutherford's lab, through the scattering of alpha particles on a gold foil, that atom actually is made up of a positively charged nucleus and electrons revolving around them. Of course, Bohr and Sommerfeld told that electrons cannot revolve in any arbitrary orbits, but in something called stationary states, so that they do not fall into the positively charged nucleus. Now, so at that point, we had a positively charged nucleus and an electron making up the matter that you see around. Subsequently, it was found that the nucleus is made up of nucleons. One of them is proton, which is a positively charged particle, and a neutral particle called neutron. So at that point of time, any matter that you saw is made up of electrons, protons, and neutrons. When people repeated a Rutherford type of scattering experiment on a proton, that means now shooting an electron to a proton, and then found that proton is actually made up of quarks and gluons. So at this moment, the quarks, gluons, and electrons sort of make up all the matter, anything that you are seeing in this, any visible matter. So those, we are talking about how these particles got mass. What was the origin of mass of these particles? Now, before that, I must say that how did we find out what is this matter made up of? How did we build on this microscope which goes smaller and smaller in length scales to see what is matter made up of? I mean, even cells are made up of quark, gluons, and electrons. This concept was given by a young physicist who was about 23, 24 years old, and it was his PhD thesis. This is D. Broglie. What he said that the dual nature of matter exists. That means it reflects particle-like as well as wave-like properties, of course, one at a particular time. And he gave this expression, lambda, which is the wavelength, which is associated with wave properties, is related to particle properties, where P is the momentum. Momentum roughly is mass times, of course, in non-relativistic case, mass times velocity, through this expression. What does this tell? That if you shoot higher momentum particles, you will probe smaller length scales. Lambda represents length scales, and momentum is sort of energy. So that was the technique which was used by physicists in order to see the fundamental constituent of matter. Probe matter with highly energetic particle because you can probe smaller length scales. Okay, and that's how we saw. So let's try to find out, how did electron get its mass? Now, to answer that, let me try to put it in a context. Of course, Newton said that mass is a fundamental quantity. It's the quantity of matter. But the question is, we all know electron has a mass 9.1 10 to the power minus 31 kilograms. I mean, in normal life, you wouldn't worry about this mass, and perhaps you would like to take it as 0. 10 to the power minus 31, that means 0.00000. So many zeros, 9 kilograms, and it sort of has, in a common perspective, may not have a meaning. But let's see what happens if electron had exactly mass 0, not 0.00, some 30 zeros, 9 kilogram. Here is this expression from Einstein's sort of relativity. And if you have a particle with finite energy, this is the expression for, so E is equal to m0 c by root over 1 minus v square by c square. Now I'm saying electron had 0 mass, so the m0 is 0. Then how will this equation be satisfied? This equation, E times root over 1 minus v square by c square is m0c, which is 0, can be satisfied only when v equal to c. That means electron, like photons, which do not have mass, would move with speed of light. If electrons were moving with such speed of light, then how are we going to form atoms? In the other extreme, let's take, we have a electron of mass instead of minus 31 kilogram. If it had 1 gram mass, then what would it be? Just to give an analogy, this is the Bohr radius, and you can see the mass of electron comes in the denominator. So you can very well imagine what would become the radius of the atom, whether you increase the mass or you decrease the mass further. The world would be very different, right? Atoms would look different. If it had smaller masses, then you may have some bigger radii, and if you have larger mass, you will have smaller radii. Things would have been very different. So it's a very fundamental question that who gave this electron this mass? Because it has the exact mass so that we can see this universe in proper proportions as we are used to. Otherwise, it would have looked very different, or maybe things would not have existed. So people postulated theories in order to understand the origin of mass of these fundamental quantities like electrons or the quarks. And they said that, okay, you will understand origin of mass due to mass being generated through interaction with a field. But experimentally, you can prove this concept if you discover a new particle called Higgs boson. And that's why the Large Hadron Collider at CERN was built to discover this Higgs boson. Now, this concept of generating mass is a little tricky. So I will be now using analogy to explain this. I mean, they are not the perfect explanations, but it is close approximation. So for that, first we have to understand what is a field. So what I will do is I will again, as I said, this is an analogy in order to explain these concepts. So we will treat wind as a field. Wind is something which we are all familiar with. Wind is something which exists everywhere. Some places you may not see it. It's dead calm. So it's sort of zero. Some places you find there is a steady breeze. So it is non-zero. It is associated with a wave. We will call it sound waves. That's how sound waves move. And if it's a quantum field, then remember every wave is associated with a particle. So what's a field? Again, I'm using analogy. It's something which exists everywhere. Somewhere it is zero. Somewhere it is not zero. It is associated, it has a wave, and it's associated with a particle. Let's take the example of a field which we sort of little bit more familiar, electric field. Does it exist everywhere? Yes, my mobile phone is working everywhere. Somewhere it is zero. Yes, I do not feel it. But when there is interference, when you are watching television, if there is interference of signals, you see its effect. Or as this girl put the hand inside a socket, which you should not do, then all the hairs stand up. Okay, so the field exists. Somewhere you don't feel it, somewhere you feel it. Please don't try this. It's associated with wave, which is the electromagnetic waves, light, and wave has a particle, which is photon. So field is something which exists everywhere. Somewhere it is zero, somewhere it is not zero, associated with a wave and has a corresponding particle. So also is the Higgs field. Higgs field is something which existed everywhere. Somewhere is it zero, somewhere not zero? No, the difference is it is not zero. If it were zero, then particles wouldn't get mass. It's associated with a wave, Higgs wave, and the particle is Higgs particle. So if we discover Higgs particle, we know that this concept of Higgs field exists. And that's where the search moved. Now, how mass is generated? Again, I will use an analogy. Now, when this Large Hadron Collider, whose properties I will mention, again, a technological marvel, was been built. Of course, it is from the taxes paid by people all over the world. It costs, as you see, is huge. And the natural question was, when we are using taxpayers' money for knowing something which could be as profound as related to our existence, origin of mass, but still, can we explain it to public in a very general way? So there was a competition of what can be the best sort of way to explain. And this set of cartoons, which was made by Professor David Miller, won the first prize in UK, this competition. And I will walk you through this explanation of how mass is generated. So what you see here is a room full of, say, political activists and important personality enters, prime minister, walks in. What do you expect? You expect that people will try to greet the prime minister, interact, share their issues. So what would happen is this. Okay? So imagine the room is the Higgs field and the particle enters the field. More it interacts, more is the mass generated. That's what you see, interaction. The interaction leads to generation of mass. Here, the important personality is surrounded by a cluster of people, and that is analogous to generation of mass. So interaction leads to generation of mass. Now, how is this Higgs particle created? Let's come back to the room. This is sort of the field we are talking about. Remember what I said about the field in an analogy with the wind. What are the properties? Now, there is some rumor. The one which I usually say is that, Sachin Tendulkar has returned back and is scoring a 100. Then what would happen? People will start to cluster around, try to see where this event is happening, try to follow that, right? So the field interacts and leads to production of this Higgs boson. So if we discover this Higgs boson, it shows sort of existence of the Higgs field, and then we know how different particles, fundamental particles, got their mass. Electrons interacted less compared to the quarks, so it got less mass. The different quarks interacted at different levels and they got different amounts of mass. That's how the masses were generated. Now, in order to discover this, we had to build one of the largest accelerators in the world, which is called Large Hadron Collider, or abbreviated as tAcT. It's situated across Switzerland and France, and it has a circumference of about 27 kilometers. It has superconducting magnets, about 9,300 of them, which has to be kept at a temperature of minus 271 degrees centigrade. Remember, water boils at 100 degrees centigrade, ice is at 0 degrees centigrade. This is negative 271.3 degrees centigrade. You need to achieve that technology in order to have this experiment succeed. The beams will go through a atmosphere where it is devoid of any other particles, so that whatever you want for interactions to happen, whether it is 2 protons or 2 ions, that is what will happen. The pressures are 10 to the power minus 13 atmosphere. 1 atmosphere is the pressure what we experience. It is 10 to the power 13 times smaller, 10 times smaller than the pressure on the moon. Imagine the technology needed to get that going. Now you want to create a large energy density in or a high temperature system. You want to mimic something which had happened early, something which had happened when this Higgs field gave masses to the particles. So you have to accelerate protons which are collided in this Large Hadron Collider at high speed. You know, a proton travels this 27-kilometer circumference 11,245 times a second. And the temperatures that are reached in these collisions are 100,000 times the temperature of the sun. I will show you an analogy. The data that comes out would fill up 100,000 dual layer DVDs every year. And then people try to look at this data and try to figure out whether Higgs has been produced, Higgs boson. Idea is the energy mass equivalence. You pump in energy and you expect that a particle like Higgs, if it exists, comes out of this system. So how hot is the matter at LHC? Just to give you a perspective, on the top side is on the top right hand side is how the universe evolved, the popular picture from the Big Bang model. And you can see there are three quantities during the evolution. One is time, another is temperature, the other is energy. And you can see in a microsecond old universe, the temperatures were of the order of 10 to the power 12 to 13 degree Kelvin. I've also given here some conversion of Kelvin, centigrade, and Fahrenheit so that when I show you this analogy, you can follow. I'll be telling in units of Kelvin. This is sort of the coldest, lowest temperature sort of recorded. This is the temperature when you trap ions, 10 to the power minus 6 degree Kelvin. This is the temperature of the universe, which is obtained by looking at the black body radiation from the cosmic microwave background radiation. This is typically the order of temperature in the rooms where you all are sitting, 300 degree Kelvin. This is the temperature from the surface to the inner core of the sun, 6,000 to 1,000,000 degree Kelvin. If you have a thermonuclear explosion, it will reach temperatures of 10 to the power 9 degree Kelvin. And what this machine is able to do is create temperatures or energy densities, equivalent energy densities of the order of 10 to the power 12 or more degree Kelvin. And then you expect that if Higgs particle exists, it will come out of these collisions and you will detect. So what I will show you is now a video, and you will see how this entire process of collision takes place. Data gets, the particles come out of the collision and hit the detectors. Then you try to transfer this information from the detectors to the computers. The computers then simulate it and construct it, which is two protons colliding. And from this event, you try to figure out whether Higgs particle exists. One of the channel is this particle is hypothesized to decay into two photons, and you try to detect the two photons which has come from the decay of this particle, and then use the mass energy equivalence, the relativistic energy formulation E square is equal to m square c to the power 4 per p square c square in order to get the mass of the Higgs particle. So that's how this video will go. So remember, it's a boson. It is named after our own Indian scientist, Satyendranath Bose. And these are a class of particles which have zero or integral spins. And the other class is fermions, and Higgs is a boson. So let me walk you through this video. So this is, we are now going to CERN, which is situated in Geneva, across Switzerland and France. This is the Large Hadron Collider ring, 27 kilometers. We start with a bottle of hydrogen. Ionized hydrogen is a proton. And these hydrogens are first accelerated in a linear accelerator. Then it's further accelerated protons in a proton synchrotron booster. When it goes to certain energy, it goes fed to a larger ring, which is called the proton synchrotron, where it is accelerated further to a higher energy. Then it is fed through a transfer line to the super proton synchrotron, and it is accelerated to a still higher energy. This is where I did my PhD, using that facility. Then it is fed to the Large Hadron Collider in two clockwise and anti-clockwise directions. The protons come and collide at the center of the detectors. And there are these experiments, Alice, Atlas, CMS, LHCb. This is the center of the detector. The particles come and collide, protons, and then particles get detected in the detectors. The data is transferred, digitized, transferred to the computers. And from the data center, it is accumulated. It needs huge amount of computing resources. As a result, one has to link the computing facilities across the globe, which is called as the concept of grid computing. You can see India participates in it. All the computing resources are pulled together, and then this is the event. You reconstruct the event to find out the two photons which Higgs may have decayed. Book a histogram where y-axis is counts, x-axis is the mass, and you can see this small peak. You can see this small peak here. This was the initial data. Now the peak has become more pronounced, and that reflects the peak is the scientific way of telling existence of a particle. And you can see if you drop down to this peak, its mass is about 125 in a unit GeV. That is approximately 125 times larger than mass of proton. The statistical significance of this, that is how good is the signal, it was with 95% confidence level when it was shown on 4th of July 2012. But now the precision is there, and that is how the Higgs got discovered at LHC. Okay. So that is the story about Higgs boson discovery. And remember, as I discussed, we discovered the particle, and then you can associate it with the field, and how electrons, quarks got their mass. They got it through interaction with the field. Of course, it attracted worldwide attention, and Nobel Prize was given to the theorist who hypothesized this concept for the theoretical discovery of mechanism that contributes to our understanding of origin of mass of subatomic particles, electrons, quarks. And the experiments which discovered it were also mentioned in the citation, which recently was confirmed through the discovery of the predicted fundamental particle by Atlas and CMS experiments at CERN's Large Hadron Collider. So that is the story of origin of mass. Now to the last one, about seeing and is believing, that is photographing of a black hole. Now this is an object from which nothing escapes. So a little simpler way to sort of understand is it's an object. You have come across this top left-hand side escape velocity relation. So what I will do is just replace this V by C so that nothing escapes out of the object. And you can figure out that sort of the mass and the combination of mass and radii, which will lead to this concept of nothing is escaping out of these black holes. Actually, the centers of galaxies are expected to have a black hole. Now, it's so far away. How does one see it? And that challenge was taken up by the Event Horizon Telescope collaboration. The concept was very interesting. Of course, it needed to get an idea about equations related to general relativity, doing simulations of various kinds, comparing with data, and then arriving at this picture of the so-called black hole. So the concept is that the event horizon of a black hole is the ultimate boundary. Right? Nothing from within it can escape out. So what people try to capture is the ring of fire that you see in this event horizon telescope image is the light of gas falling into the event horizon. Okay, so and nothing can come outside this event horizon. So as a result, you see this ring-like structures, and in the illuminator side is actually gases falling into the event horizon. So using this event horizon telescope, scientists obtain an image of black hole at the center of the galaxy. This particular case was called as M87. And this was outlined by the emission from the hot gases which are swirling around it under the influence of strong gravitational force near its horizon. That's how it pictured. But it also needed a tremendous amount of physics ideas, technology, and almost putting telescopes across half of the Earth. So let me show you. Yeah, if this is the Earth, you can see the points where the telescopes were switched on in order to get to focus on to this particular M87 galaxy, and then you could picture out these the photograph of the black hole. This was done by the Event Horizon Telescope collaboration. However, for the theory of black holes, Nobel Prize was given in 2020 to scientists here, Roger Penrose, Reinhardt, and Andreas. So that is photographing of a black hole. So let me come to my summary. Actually, this last 10 years, we are lucky to be in this decade to see these three most very profound discoveries or events. One is discovery of Higgs boson on 4th July 2012. It was announced in the CERN auditorium, which has led us to understand the origin of mass. For example, why electron mass is what it is. If it would have been zero, or it would have been heavier or slightly lighter, the world would have been very different. On 14 September 2015, the gravitational waves were discovered. That helps us further in understanding the theory of gravity as given by Einstein. And of course, his ideas of general relativity was used to see a black hole or photograph a black hole, which occurred on 10th April 2019. There are, of course, many other exciting topics which is out there to be discovered. I will not have time to go into details of that, but I will end with a quote for the young people, young minds, from the founders of Indian Academy of Science, Professor C.V. Raman. So youth is the most glorious time of all. Sorry. I think he was giving this in the IIT convocation time. Told elsewhere that most of the great discoveries in science have been made by young people. It is not the experience or wisdom that the old age brings, but the freshness of outlook, the indomitable desire to achieve, which is the characteristic of youth, that makes discoveries possible. It is this that makes life worthwhile. If only you realize this and realize that here I am still young, let me see what I can do. that all discoveries become possible. I hope you will be inspired by these words of Professor C.V. Raman. This is your time, and there are many other things, mysteries of the nature yet to be discovered. So thank you very much. I will end with these references of experimental findings of Higgs boson, gravitational wave, and photographing the black hole. These are the scientific papers associated with it. Thank you.
Thank you, Professor Mohanty, for a very inspiring talk. This probably is the first time I understood what happens at LHC. We have time for some questions, and I see a question in the chat which says, "How are supermassive black holes formed?"
Yeah, so these are sort of research topics where all answers are not yet known. So it is an evolving topic. There are some ideas, and also it is not directly related to my field. So there are different concepts, but all I know is the centers of galaxies have this object, which is a black hole.
I think there is a further question coming. Is the cyclotron used at LHC to accelerate?
It's a circular accelerator, not exactly cyclotron. There has to be some synchronization done so that the protons at a particular energy is circulated. Yeah, the concept is similar. Yeah, the gravitational waves are moving with the speed of light.
There's one Pawan Kumar asking, black holes neither become small nor large. Any confirmation on that?
I don't know about that. Maybe he's giving a comment.
Which has been told by apparently Stephen Hawking.
I see.
Yeah.
Okay, I don't see any further question. I have a comment. There are fantastic recollections by S. Chandrasekhar on Eddington. It's a very, very pleasurable reading. And what I wanted to mention is Eddington was also an avid cyclist, and he designed a number. So the definition of, let's call it Eddington number. Eddington number is n for anyone, say for me, if I have cycled n miles on at least n days. And Eddington's own Eddington number was 77. That means he had cycled at least 77 miles or more on 77 different days. Now this is a remarkable feat, at least in those days when roads were not good and accommodation was not easily available. Okay, one more question. Can we relate production of conservation of energy?
Well, in any process, energy has to be conserved, whether you generate particles or waves. So,
all right, I think we are nearing 6 o'clock. I think a minute to go. Thank you very much, Professor Mohanty, for a very enjoyable talk.
Thank you.